Hello everyone, I am Devashish Das, Assistant Professor of Greater Kolkata College of Engineering and Management GIS Group. In this today's session, we'll discuss on the MOSFET. The MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. MOSFET is a kind of a transistor. That means a transfer resistors. That means we can change the conductivity of a transistor with the help of some input voltage or current. The MOSFET is mainly operated in field effect. That means if we apply electric field, that means electric voltage is applied mainly on the gate and the current can be controlled in between source and drain. So we'll see how this operate and what are the characteristics of this MOSFET in this today's session. So let us begin. So it is a structure of a MOSFET. There are four terminals mainly. You can see over there. It is a source, it's a drain, one is gate, one is body. It is a n-channel MOSFET. That means the body is p-type and the channel which is formed under the gate is n-type when it is in conducting state. That is why it is called the n-channel MOSFET, and the source and the drain are of heavily doped n-type material, and in between gate, source, drain, there are each of this terminal there is a metal contact. The black color is of metal. So in the case of the gate terminal, the metal contact is there, but under the gate, the metal contact, there is a silicon dioxide layer, a layer of silicon dioxide, which is a kind of insulator and which prevent the current flow from gate to body. And this insulator also play a capacitive role. That means a dielectric material and act as a dielectric and form the n-type channel under the gate. So when a gate voltage is present, the minority carrier of p-type material, which are electron, they are gathered and form a channel under the gate and produce a bridge from drain to source. And whenever the source to drain voltage is given, the electron starts to flow. In general, source is kept negative and drain is kept to positive. For that reason, the electron flow from source to drain and the current flow occurs from drain to source. In this way, the MOSFET works. So the gate is made of metal. There is an oxide layer, the silicon dioxide. That is why it is called the metal oxide. And the field effect means whenever we apply a voltage in gate, a field is created to pull up the electrons in the substrate region and make a channel. That is this why called the field effect. It means the field, electric field, whatever the electric field we apply at the gate, that electric field produce the channel and make a control of this device to make a current flow from source to drain. It is the beauty of this transistor, the metal oxide field effect transistor. And as the gate current is zero, as there is no physical gate current is occur, and only the voltage is being used to control the channel. That is why the power consumption of this device is very low. That is the beauty of this device, and we'll discuss more on it. Let us begin. MOSFET can be obtained in the form of IC in the market, which is easily available for power handling capacity. A metal portion is there to dissipate the heat. It's a kinds of IC. There are lots of ICs. It's a one kind. It is a symbolic representation of the MOSFET. MOSFET are of four types. They are basically divided into two categories: enhancement mode MOSFET and depletion mode MOSFET. And each of these category, there are two types of MOSFET, that is P channel and N channel. That is why there are total of four types of category of MOSFET, which is symbolized in this picture. You can see the Q1, Q2, Q3 and Q4. These are the four MOSFET, and Q1 is enhancement mode type MOSFET. It is a N type, and Q2 is enhancement mode type MOSFET and it's a P type, and Q3 is a depletion mode type MOSFET, which is N type, and Q4 is the depletion mode type MOSFET and it is of P type. So these are the four types of MOSFET, and they are the representation of the symbolic representation of each of these type. The body is connected. This is the fourth terminal, which is represented the type of the MOSFET, which is N type or P type. It's called the body terminal. You can see in the four cases there are the body terminal. This body terminal mainly connected with the source terminal. So the body and source are the common terminal for these four types of MOSFETs, and they are make it one. Body and source add together and just make them one source terminal. So in this way we can identify the MOSFETs, which are the type and symbolic representation of the MOSFET. Now see, now we are slowly going towards the IV characteristics of the MOSFET. So first we discuss some channel resistance and the current through the MOSFET. Then we are going towards the IV characteristics. So in this slide you can see it's the Ohm's law, the current through the channel. It's a V equal to IR and I is V by R. So it is the representation of the current, where V is the drain to source voltage. Here you can see in this picture, it's a source, it's a drain, it's a gate. A potential is applied between source and drain with the help of this voltage. You can see it is VDS, which is drain to source voltage, which is represented as V over there, and another voltage which is known as the VGS, which is source to gate voltage. In this picture you can see this is a small voltage which is applied across the gate to source terminal, and it is denoted as VGS. The length of the channel is the important thing. Between source and drain, the length of the channel is represented as L, which is the length of the channel or the gate length. Both are the same almost. In this picture we applied the V is very less than VT. VT is the threshold voltage. We will discuss what is threshold voltage will be. The channel resistance R, W is the width of the device, can be represented as R equal to rho L by A. So length by the whole thing, it is Qn mu A into W. W is the width of the channel, Q is the mobility of the charge, and Q is the charge, where Ns equal to Ci by Q and Vg the channel current is represented as I, and I is V into Q into Ns mu W by L. If we simplify it and make it Vq mu W Ci upon Q, it's a capacitance of the channel, gate capacitance Ci, and Vg minus Vt divided by L. So I equal to, we can find with the help of this simplification, is I, the drain current, is mu by W Ci into Vg minus Vt into V by L. V is the total voltage applied across the drain to source, and Vg is the gate voltage. Vt is the threshold voltage. Threshold voltage means the minimum voltage applied to form the channel in between source and drain. Whenever the gate voltage is applied, the electrons from the substrate are accumulated under the gate, and for the minimum voltage to form this channel in between source and drain is called the threshold voltage. And after the threshold voltage, the current begins to flow between the source to drain if source to drain voltage is applied already. So in this way we can find out the current, total current, which is flowing in between the source to drain, which is represented at I. Mu is the mobility of the electron, and the W is the width of the transistor. The transistor is used in this equation, and Ci is the oxide capacitance under the gate, and Vg is the gate to source voltage, Vt is the threshold voltage, V is the total voltage applied across the drain to source, and L is the channel length in between the source to drain. So in this way we can represent this current modeling and the current of this transistor. So we'll move forward, and there is one term called the transconductance. It is the most important thing of a MOSFET. With the help of this transconductance, we can characterize the MOSFET. Transconductance is the in the MOSFET application, and input signal is the gate voltage Vg, and the output is the drain current Id. The ability of the MOSFET to amplify the signal is given by the output to by input ratio, is called the transconductance Gm, and Gm is the transconductance, and it is the denoted by delta Id by delta Vgs. That means the rate of change of the drain current with the respect to the gate to source voltage is known as the transconductance, which is denoted as Gm. Can we know the ID? We have previously discussed about it. The ID is given like mu into W into Ci into Vg minus Vt into V by L. V is the drain to source voltage. From that equation, if we simplify this Gm and make a derivative of it, of this equation, we'll find the Gm, and Gm is represented something like this: V into mu n into W into Ci divided by L is the length, V is the drain to source voltage, mu is the mobility, W is the width of the transistor, and Ci is the oxide of this transistor, gate oxide. So the key factor affecting the FET performance, that means what is the impact if mu mobility is increased, the I and GM will also increase with the help of this. If L is decreased, then I and GM will also increase. So these are the factor to increase the GM and also I. So if we increase the mobility, that means for the electron and the hole, the electron mobility is higher than the hole, so the performance of the transistor will also increase. From this equation we can conclude about it. If L means that the length of transistor, that means if we decrease the length, we also get a reflection of it in the drain current I and GM. That means you can get a better performance of these devices. Higher carrier mobility mu and the short gate length L are key features of a FET. So in this way we can see the impact of the GM on mu and L and whatever the parameters is used. In this picture we can see the picture of a MOSFET, a physical MOSFET, which is used in different circuit. They are very tiny in nature. They are as tiny as less than the thickness of a hair. So if we want to see this MOSFET in physical domain, we have to use a microscope or a higher version of X-ray microscope and other things to find out the source, drain and gate. You can see this is a tiny, say, gate, it's a source, it's a drain, and it's a X-ray picture, microscopic picture of a MOSFET. So this is all about the MOSFET for today's session. You can see N channel, P channel MOSFET. MOSFET can be used as a driver in case of power electronics. The MOSFET can be used for heavy current applications. They can be used for drivers, driving motors, and in power electronics they can handle lots of megawatts of power, kilowatts of power, kilowatts, megawatts of power. So this is all about the MOSFET. You can see it is a basic circuit diagram of a driver. A 5-volt signal is given towards the gate to form the channel, and this signal came from the microprocessor, microcontroller, which is not capable to switch on the driver directly. So this is called a digital signal. A digital signal is very weak and they cannot turn on the motor driver directly, so, or heavy load directly. So we apply this driver, MOSFET driver. So if we apply a digital signal in the gate and the MOSFET is turned on and the channel is created under the gate, and if we apply this source to drain voltage with the help of this motor in series, you can see it's a 24 volt is applied across this. So a current flow from drain to source and the electron flow from source to drain. So in this way we can apply this MOSFET in case of driver circuits. Is a kinds of application type of switch, and we will discuss more on it in our coming sessions. So that's for today. We'll just end over there and we'll see what are the next. So thank you very much. That's for today. Thank you being with us.